In this video, we'll talk about statistical significance and type 1 and type 2 errors. So starting with statistical significance, it's very common in stats courses to cover testing a null hypothesis that looks like this, or maybe like this for the proportion case, where the 1 and the 2 refer to different groups or subpopulations. So maybe you want to test that the average earnings is the same for men and women, or the average poverty rate is the same in urban and rural areas, something like that, where there's, again, two different subpopulations, urban and rural, for example, and you're testing the null hypothesis that some parameter is the same in the two populations. I'm not a big fan of the tests like this because they can be accomplished in a simple regression, right? What we can do is just run a simple regression where y is your variable of interest. So this could be like a poverty indicator or earnings levels or something like that. And x is an indicator for being in one of the groups. So this could be a female indicator, it could be a rural indicator, or whatever. And based on our study of simple regression, this is a saturated model. The beta 1 hat is going to tell you the difference in the average value of y across the two groups. And so you can just test the null hypothesis, beta 1 equals 0, which would be a quality of average y across the two groups in this case. And if you reject that null hypothesis, it's exactly the same thing as rejecting one of these null hypotheses, okay? And the advantage of this is starting from a simple regression lets you then think about, well, what if I wanted to test basically the same hypothesis, but like controlling for some other variables? Simple regression allows you to do that in a way that, these forms of the hypothesis test are just necessarily very limited, okay? So that's our starting point, is if you want to test for a quality of mean or proportion across groups, just set up a simple regression and test whether the slope is 0, the coefficient on that group indicator. If we reject this null, then we say that the difference in the average y between the groups is statistically significant. So if we put a poverty indicator, individual level data. So y is a poverty indicator, x is a rural indicator, and we reject this null hypothesis when we run the hypothesis test. We say there's a statistically significant difference in poverty rates between urban and rural areas, for example. Okay, and this again extends really naturally to multiple regression. So now you want to, let's say, control for some things. So you say, well, now I want to control for like the amount of education and the race ethnicity composition of urban and rural areas. So I'm going to add those controls to the model. Now, holding those things fixed, is there an urban-rural difference in poverty rates? Basically, you just run the regression with the controls, and then you do effectively a hypothesis test that looks really similar, but you might have a different estimate of beta 1 in that case after adding the controls. Okay, so that's essentially how I would frame the idea of statistical significance within our course, is just set up the appropriate regression, and then you're testing a null hypothesis about a regression parameter. Okay. Another thing I want you to keep in mind, though, is that I think statistical significance, while it's important, is sometimes overemphasized. So statistical significance of your estimate beta 1 hat is distinct from beta 1 hat being meaningful, like of a large magnitude in the context you're studying. So we'll talk about some examples of this in class. But for now, I'm just trying to make the point that if you imagine the poverty rate example, so you run a regression of like a poverty indicator on a rural indicator and some controls, okay? If you have a really large sample, then a small difference in poverty rates can be statistically significant. And if you have a really small sample, a large difference in poverty rates can be not statistically significant, okay? And you just want to think sort of holistically, both considering the actual difference in estimated poverty rates and the uncertainty or sampling variability around that, right? And not just boil it down to, oh, there's a significant difference or there's not, because the magnitude of the difference really matters a lot too. Okay, that's the point I'm trying to make. All right, the other thing I wanted to do in this video is to talk about type 1 and type 2 errors. So these are both ways that our hypothesis test decision can be wrong. Okay, a type 1 error means rejecting the null hypothesis when it's true, sometimes called a false positive. A type 2 error is if the null hypothesis is false, and we didn't reject the null hypothesis. So one thing I want you to see straight away is that type 1 and type 2 errors apply in different states of the world. You can never make both a type 1 and a type 2 error, because a type 1 error is something you're at risk of making when the null is true, and a type 2 error is something you're at risk of making when the null hypothesis is false. Okay, so you're only in one of those two states of the world at any given time. All right. An analogy that's often given here is a criminal trial. Right. So in the U.S., in a criminal trial, defendants are supposed to be presumed innocent until proven guilty beyond a reasonable doubt. All right. And what we're doing there is we're setting up the null hypothesis as innocence. And most people would think that making a type 1 error in this case, which is finding an innocent person guilty, would be a serious injustice. And so that's the idea of having a really high sort of burden of proof for the prosecutor that's making the case beyond a reasonable doubt. All right. What we're doing in that case is we're actually trying to set a really low value of alpha, the significance level. Okay. Because it turns out alpha is the probability of a type 1 error when the null hypothesis is true. So I carried over our plot here from when we talked about the critical value method. This is our test statistic distribution under the null hypothesis, centered at 0 here. And you know that the critical value method sets a critical value and a negative counterpart that puts total probability alpha in the tails of the distribution. All right, so across possible samples, you're pulling an estimate, and therefore a test statistic t, from this distribution. And with probability 1 minus alpha, when the null is true, you get a test statistic that's close enough to 0 that you don't reject the null. But with probability alpha, you get weird-looking evidence that leads you to reject the null. If you think that rejecting the null when it's actually true is a really bad thing to do, as it would be in a criminal trial, then you want to set a really low value of alpha, which means taking the critical value and moving it further into the tails. So that's the idea of the beyond a reasonable doubt. Okay. A type 2 error in this case, remember, this is something that we are at risk of making if the null hypothesis is false. So this would be our null is the defendant is innocent. Null being false would be the defendant is actually guilty. And the type 2 error here is not rejecting the null. So the person's guilty, but maybe the evidence against them wasn't strong enough, and so we find them not guilty at the trial. Okay. And this is an injustice in its own way, but typically people treat that as sort of a less serious injustice than a type 1 error in a criminal trial. All right, so that gives you a sense of type 1 and type 2 errors, and it'll take us a while to develop the idea of how you could find the probability of a type 2 error, but hopefully you followed the explanation of why the probability of a type 1 error when the null is true is just alpha.